Hello everyone, my name is Bryan Wang. I am a PhD student at the University of Toronto. In this video, I will introduce enabling conversational interaction with mobile UI using large language models. This work was done during my internship at Google Research with my mentors Gang Li and Yang Li. Conversational interaction allows users to efficiently communicate with the computing system and is useful when other input modalities such as touch are unavailable. It is also a long-standing pursuit of HCI research for decades. Nowadays, users can already ask smart assistants to perform simple mobile tasks such as setting an alarm. However, existing assistants are still quite limited in the interactions they support. For example, they may not be able to answer users' questions based on screen information or summarize the screen. This type of interactions typically requires a computational understanding of GUIs, which is absent in the current assistants. Recent work in HCI and machine learning has investigated technical building blocks to enable conversational interaction with GUIs, such as summarizing or captioning the UI or mapping users' language instruction to UI actions. However, each of this work only addresses a limited aspect of conversational interaction, yet requires considerable effort in curating large-scale datasets and training specialized models just to enable a single interaction capability. A lightweight and generalizable approach to enable conversational interaction is missing. Recently, large language models, or LLMs, such as PaLM and GPTs have demonstrated impressive ability to generate sophisticated text, perform reasoning, and even adapt themselves to various tasks. Adapting an LLM to different tasks can be done with the so-called few-shot prompting. For example, if we prompt the model with a few examples of English to French translation, it will learn from the context to perform the translation. Because few-shot prompting only requires a handful of data to learn a new task, it allows us to quickly prototype new models for various tasks. Seeing this exciting opportunity, we investigated in this paper the how-to and effectiveness of prompting large language models with UIs to enable various types of conversational interaction. Now let's first talk about how we prompt large language models with mobile UIs. We propose a depth-first search, or DFS, algorithm to convert the view hierarchy data of the mobile UI into HTML syntax. The view hierarchy is a structural tree representation of the UI containing various properties such as the UI classes and the element locations. Our key insight is that because LLM's training data has many HTML data, converting the view hierarchy to HTML will help the model better understand and process the UI. Here's an illustration of how we construct the few-shot prompt. We first put in a task instruction. Here we use screen question generation task as example. Then we select the first mobile UI example, generate the screen HTML, and put it into the prompt. Next, we create the task output, in this case the questions generated from the UI input, and we put that in the prompt. Now we have the first data example, or shot. We then repeat this process again for the second UI example. Then we have a prompt with two data examples from this task. With this two-shot prompt, the model can already learn how to perform the task. Note that the task instruction only needs to be provided once. When we have a test screen that we want the model to generate question, we will again convert it to the HTML and append it to the end of the prompt. After that, we send the whole prompt to a large language model, and the model will then predict the task output for the task screen. So how do we generate the screen HTML? Firstly, we map the Android UI classes to the equivalent or similar HTML tags. Text view to a p tag, button-related classes to a button, image-related classes to an img tag, edit tags to input, all the other classes such as linear layout to the div tag. Then, we insert attributes to the HTML tags by converting Android properties to the HTML attributes. We map text to inner text, resource ID, which contains element information written by the developers, to class, content description to alt text, and the DFS element order to ID. Our algorithm only generates HTML for the leaf elements, which are usually the elements that users can see and interact with. So here's an example of screen HTML generated from the create password UI on the left. An example task output for screen question generation. It teaches the model to generate questions asking users to provide password, hint, and email based on the UI. Combining all these elements together, our prompt has a task instruction, screen HTML, and task output. This is well enough for many UI language tasks. However, we found that more complicated tasks may benefit from logical reasoning about the screen. Therefore, for those tasks, we further incorporated the chain of thought prompting that can improve LLM's logical reasoning ability. Essentially, it's breaking the task into several intermediate steps to generate before the final output. For example, we asked the model to first identify how many input tags on the screen, the purpose of the UI in each input field. These intermediate results can provide more context and help ensure the model do not skip input tags when generating questions. Note that if chain of thought prompting is used, the model will learn to output both the reasoning steps and the task output. We tested the feasibility of our approach with experiments on 4 language UI tasks and compared our method with baselines. 2 of them have prior benchmark models trained with hundreds and thousands of data, while for the other 2, we are the first to test them in literature. For all the tasks, we used at most 2 examples to construct the few-shot prompt. The first task is screen question generation. Given the mobile UI, generating question asking for specific information related to the input fields. We developed a template-based method to generate questions based on resource ID. The baseline can already generate somewhat relevant questions. We found that LLMs are able to use the full screen context to generate high-quality questions. We conducted a human rating study, and the results showed that the LLM generated questions with near-perfect grammar and higher relevance to the input fields on the screen. We also found that LLMs are able to combine relevant input fields into a single question. For example, combining the filter inputs for the minimum price and the maximum price into a single question, what is the price range? This ability can enable more efficient communication. The second task is screen summarization. Given a screen, summarize its purpose and main functionality. The task was originally proposed in our prior work published at WIS21, which proposes a benchmark model screen to words. We compared our LLM approach with the benchmark model. We found that LLM uses more screen details to generate screen summary, while screen to words tend to generate more generic summaries. Interestingly, LLMs can use their prior knowledge to help write the summaries. For example, the right screen does not contain the word London Tube, but the LLM inferred the stations belong to it. When evaluated against token matching metrics reported in the original paper, large language model generally underperformed screen to words. This is inconsistent with the summary quality that we observed. Therefore, we conducted a human evaluation asking annotators to vote between LLM and screen to words summaries. The results showed that LLM summaries are way more accurate than the screen to words model trained with massive datasets. This shows the limitations of existing metrics on properly reflecting the human perceived quality of summaries. The third task is screen question answering. Given a UI screen and a question, the model needs to generate answers based on the screen information. We tested with a small screen QA dataset and found that LLM was fairly capable of generating correct answers. In our evaluation, LLM significantly outperformed DistilBERT, a standard text QA baseline model, achieving more than 60% of fully correct answers. The zero-shot LLM already achieved more than 30% of exact matches score, showing the model's intrinsic ability of question answering. The last task is mapping instruction to UI action. Given a screen and a user instruction, the model needs to identify the UI element to perform the corresponding UI action. We use the Pixel Help dataset, which contains interaction traces for tasks such as turn on Wi-Fi. Each trace contains multiple steps, and each step contains an instruction. We evaluated with the metrics reported in the original Seek-to-Act paper, partial, which means the percentage of individual steps being correctly predicted, and complete, which means the percentage of the entire interaction traces being correctly predicted. While LLM did not outperform the benchmark model trained with massive datasets, it still achieved impressive performance with only 2 data examples prompted. The key takeaway of our study is that compared to traditional machine learning workflow that requires expensive dataset collection and model training for a single interaction capability, LLM offers a lightweight and generalizable approach to quickly prototype and enable various language interactions. In future work, we plan to extend our approach to support multi-screen and multi-turn interaction. For example, with multi-screen interaction, users can input only a high-level goal instead of the step-by-step instruction, and the model will automatically infer and execute actions across multiple screens. Supporting multi-turn interaction will also help the model disambiguate and recover from errors. Preserving knowledge about prior screens and interactions will be important to achieve this class of future work. Additionally, our work only leverages the textual information of UI. However, UI also has visual information that cannot be conveyed in text alone. A natural next step is to extend our prompting approach to multimodal prompts, using models such as GPT-4 and Flamingo. Lastly, our studies and various recent work have shown the limitation of existing token matching metrics in evaluating LLM generation. It is important for future work to investigate metrics that better reflect the actual quality of text generated by LLMs. Thank you for watching this video. Feel free to reach out to me if you have any questions about the work.